Welcome! In this session, we're going to explore problem number 1256, titled Encode Number. We'll break down the problem, analyze its requirements, and discuss different approaches to solve it effectively. Let's dive in. In this problem, you are tasked with encoding a given non-negative integer, number, into a specific string format. The encoding process involves a three-step procedure. First, you calculate number plus 1. Then, you convert this new value into its binary representation. Finally, you remove the most significant bit, which is the leading one, from the binary string. The result is the encoded string representation of the original number. The input is a single integer number that satisfies the condition 0 equals number equals 10⁻⁹. The output is the encoded string corresponding to the given number. To clarify, let's analyze an example step by step. Suppose the input is number equals 23. For the input number equals 23, the first step is to add 1 to number, resulting in 23 plus 1 equals 24. Next, we convert 24 into its binary form, which is 11,000. Finally, we remove the leading one from this binary string, leaving us with the result 1000. This is the encoded string representation of 23. Another example is when number equals 0. Here, we add 1 to number, giving 0 plus 1 equals 1. The binary representation of 1 is simply 1. Removing the leading one from this binary string leaves us with an empty string as the output. Now, consider the case where number equals 107. Initially, we add 1 to number, resulting in 107 plus 1 equals 108. Converting 108 to its binary representation gives us 1101100. At this stage, we remove the most significant bit, which is the leading one from 1101100. This operation results in the string 101,100. So, the encoded string representation of 107 is 101,100. This process demonstrates how the encoding rule is consistently applied regardless of the input value. The problem also specifies some important constraints and edge cases. For instance, when number equals 0, the encoded string is empty because the binary representation of number plus 1 is 1, and removing the leading bit results in an empty string. For very large values of number, such as those close to 10⁻⁹, the solution must handle binary numbers efficiently. The problem guarantees that the input will always be a valid non-negative integer, so there's no need to account for invalid inputs. Overall, the encoding process primarily involves basic arithmetic and binary string manipulation, making it computationally feasible for all inputs within the given range. To solve the problem of encoding a number, one straightforward strategy is the brute force approach. The intuition here is to directly follow the steps outlined in the problem description. First, we add 1 to the input number, which shifts it to the next value. Then, we convert this updated number to its binary representation. Finally, we trim the leading one from the resulting binary string to produce the encoded output. For implementation, we can utilize built-in functions like Python's bin to handle the binary conversion and simple string slicing to remove the leading bit. This approach is efficient in terms of time, as the binary representation of a number depends on the number of bits required, giving us a time complexity of O log number. The same applies to space complexity since we store the binary string. The main advantage of this method is its simplicity and reliance on existing utilities, making it easy to implement. However, it doesn't provide any significant optimization beyond the direct computation process. An alternative to the brute force approach is an optimized method based on mathematical insight. Here, we focus on the key observations about encoding. Essentially, the process of encoding can be reimagined as expressing the number in a binary system after incrementing it by 1. The removal of the leading one simplifies the representation but does not alter the sequence of bits. This insight leads to a more streamlined implementation where we can avoid certain redundant steps, such as explicitly adding 1 and then converting to binary. Instead, we can use bitwise operations to directly extract the relevant portion of the binary representation. While the time and space complexities remain the same at O log number, this approach potentially reduces unnecessary operations. However, it demands a deeper understanding of binary arithmetic and bitwise manipulation, which could make the implementation more complex and prone to errors. After considering both approaches, we opted for the brute force method as our chosen strategy. The reasoning behind this decision lies in its clarity and simplicity. By leveraging built-in language features, the brute force approach minimizes the likelihood of errors, making it more reliable for implementation and debugging. While the optimized approach offers a slight reduction in computational overhead, the difference in performance is negligible. The trade-offs are straightforward. The brute force method is easy to read and implement but may involve minor overhead from built-in functions. Conversely, the optimized approach is marginally faster but introduces additional complexity. Ultimately, the simplicity of the brute force solution makes it a better option for this problem, as it strikes a balance between efficiency and ease of use. Both approaches lead to the same time and space complexity, which is O log number. This reflects the fact that the number of bits required to represent the number in binary grows logarithmically with the size of the input. In conclusion, we chose the brute force approach due to its simplicity and clarity. While the optimized method offers minor efficiency gains, those improvements are not significant enough to outweigh the added complexity and potential for implementation errors. The brute force strategy ensures a clear and effective solution to the problem, making it the most practical choice in this context. In this problem, we are tasked with encoding an integer number into a binary string representation by following a specific set of rules. The process begins by incrementing the given number. This increment is crucial because it aligns the binary representation with the encoding logic outlined in the problem. For instance, if we start with the input number 5, the first step will be to calculate number plus 1, which equals 6. This ensures that the subsequent steps operate on a modified version of the input that adheres to the encoding requirements. The goal is to derive this encoded representation as efficiently as possible, given the constraints of the problem. So, the input is an integer number, and the output is a binary encoded string derived from this process. Now, after incrementing the input number, the next step is to convert the result into its binary representation. This is done using a standard conversion method, such as Python's bin function. The binary string generated will often have a prefix, such as 0b, which needs to be stripped to isolate the pure binary form. For example, converting 6 yields the binary string 110. Once we have this binary string, the next operation is to trim the most significant bit, or MSB, which is the leftmost digit. This step is essential because the problem explicitly requires us to discard the MSB from the binary representation of number plus 1. For instance, trimming the MSB from 110 results in 10. Finally, this trimmed string becomes the encoded binary representation of the original input number, which we then return as the output. The key insights in this algorithm revolve around why these steps are effective. Incrementing the number before binary conversion ensures that the binary representation shifts appropriately for encoding. This avoids unnecessary complexity in the encoding logic. Trimming the most significant bit is another crucial step. It simplifies the binary string and directly corresponds to the encoding rules specified in the problem. This approach is not only straightforward but also computationally efficient. The entire process, from incrementing to binary conversion and trimming, operates in O log number time. This efficiency comes from the fact that the number of bits in number grows logarithmically with its value. Additionally, the algorithm makes use of integers for arithmetic operations and strings for binary manipulation, both of which are well suited to these tasks. Let's break this down with some concrete examples. For number equals 5, we start by incrementing it to 6. The binary representation of 6 is 110. Trimming the most significant bit from 110 leaves 10, which is the final encoded string. For another example, if number equals 0, incrementing it gives 1. The binary representation of 1 is 1. After trimming the most significant bit, we are left with an empty string, which becomes the output. These examples illustrate how the algorithm consistently applies the same steps regardless of the input value, ensuring correctness and simplicity in deriving the encoded representation. Finally, let's consider some edge cases and analyze the complexity. When number equals 0, the smallest possible input, the output is an empty string because the binary representation of 1, after trimming, has no remaining bits. For the largest input, number equals 10⁻9, the algorithm still operates efficiently, as the number of bits in its binary representation is proportional to log number. Another edge case is number equals 1, where the binary representation of 2 is 10, and trimming the MSB gives an empty string as the result. In terms of complexity, the time complexity is O log number, because the binary conversion and string slicing depend on the number of bits and number. The space complexity is also O log number, due to the storage required for the binary string. This ensures the algorithm is both efficient and scalable for all valid inputs. This Python implementation solves LeetCode problem number 1256, encode number, which involves encoding an integer into a specific binary format. Let's go through the code step by step. The encode function begins by incrementing the input number by 1. This is necessary because the encoding rules for this problem are based on the binary representation of number plus 1. For example, if the input is 4, we first calculate 4 plus 1 equals 5. Next, we convert the increment number to its binary representation using Python's built-in bin function. The bin function returns a string prefixed with 0b, indicating that it is a binary number. For instance, bin 5 produces 0b101. The key step is to remove the leading one from this binary representation. According to the problem, the encoded number is derived from the binary representation of number plus 1 with the most significant bit, the leading one, removed. In Python, slicing can be used to omit the first 3 characters of the bin output 0b1, leaving only the remaining binary digits. For bin 5 equals 0b101, slicing with 3 results in 01. The function then returns this sliced binary string as the final encoded result. The implementation is efficient, with a time complexity of O log number due to the binary conversion, and it handles all valid input values within the specified range. 0 equals number equals 10 to the power of 9. This concise approach ensures the solution is both correct and optimized for performance, adhering to the problem's requirements. This is the Java implementation of LeetCode problem number 1256, encode number. The logic mirrors the provided Python implementation. The method increments the input by 1, converts it to a binary string, and removes the leading one. Key Java-specific differences include the use of integer to binary string for binary conversion and explicit type declarations for method parameters and return types. In this problem, our task is to encode a non-negative integer into a binary string representation following a specific process. First, we increment the input number by 1. Then, we convert this new value into its binary representation. Finally, we remove the leading one from the binary string to produce the encoded result. Let's look at an example to understand this process better. If the input number is 0, we start with the value 0. The first step is to increment the number by 1, so number becomes 1. Next, we convert the increment number into its binary representation. For number equals 1, calling bin 1 gives us the binary string 0b1. The 0b prefix indicates that this is a binary number, and the actual binary value is 1. The next step is to remove the leading one from this binary string. After removing it, we are left with an empty string. Therefore, the encoded result for number equals 0 is an empty string. Now, let's walk through another example where number is 3. Starting with number equals 3, we increment it by 1, which gives us number equals 4. For number equals 4, we need to convert this value into its binary representation. Using bin 4, we get the string 0b100. Here, the binary representation of 4 is 100. The next step is to remove the leading one from this binary string. When we remove the leading one, we are left with 00. Therefore, the encoded result for number equals 3 is 00. Let's now examine a slightly larger input. If the input number is 23, we start by incrementing it by 1, resulting in number equals 24. For number equals 24, we follow the same process. First, we convert 24 into its binary representation. Using bin 24, we get the string 0b11000. The binary representation of 24 is 11,000. Removing the leading one from this binary string leaves us with 1000. This means the encoded result for number equals 23 is 1000. From these examples, we can observe that the encoded string is derived by taking the binary representation of number plus 1 and omitting the leading one. Smaller numbers produce shorter encoded strings, while larger numbers yield longer strings. The time complexity of this process is O log number, as converting to binary and slicing the string both depend on the number of binary digits, which scales logarithmically with the input size. The space complexity is also O log number, since storing the binary string requires space proportional to its length. When analyzing the time complexity of this solution, we focus on the two main operations involved. First, the increment operation number plus equals 1 is straightforward and takes constant time, or O1, because it simply updates the value in memory. The second operation involves converting the number to its binary representation using the bin function. The runtime of this operation depends on the number of bits in the binary form of the number, which we can denote as k. Since k is proportional to the logarithm of the number plus 1, specifically log base 2 of number plus 1, this conversion takes O log number plus 1 time. Additionally, slicing the string using 3 is directly proportional to the length of the binary string, which also results in O log number plus 1. Combining these operations, the overall time complexity is dominated by the binary conversion and slicing, making it O log number plus 1. Now, looking at the space complexity, we consider the memory used during the solution. The binary string representation created by the bin function is of length k, where k equals log 2 number plus 1. This means it requires O log number plus 1 space. When we slice the binary string with 3, it's important to note that slicing creates a view of the substring rather than duplicating the string, so no additional space is consumed for this operation. Beyond that, the space required for the integer number and the result string is constant and does not grow with the input size. Therefore, the total space complexity of the solution is O log number plus 1. To understand the efficiency of this solution, let's compare it to a naive approach. A brute force method might involve iterating through every number from 0 to number, converting each to its binary representation, and stripping the leading one. This would lead to a time complexity of O number asterisk log number, because you would process each number individually, making it significantly slower for large inputs. In contrast, the optimized solution directly computes the binary representation of number plus 1, achieving an O log number time and space complexity. This is far more efficient in terms of both speed and memory usage. Additionally, it's worth noting that the best case and worst case complexities for the current solution are identical. Since the operations depend solely on the magnitude of number and not its specific value, the time and space complexity remain consistently O log number plus 1, regardless of the input. When tackling this problem, there are a few common mistakes to be aware of. First, overcomplicating the solution can be a major pitfall. It's easy to jump into complex algorithms without first considering simpler approaches like brute force or greedy methods, which can help you gain clarity and build a foundation for optimization later. Additionally, ignoring edge cases is another frequent error. Always test scenarios like empty inputs, single elements, or maximum constraints to ensure your solution is robust. Inefficient iteration is also something to watch out for. Using nested loops unnecessarily can cause your solution to exceed time limits, especially when a linear or logarithmic approach is possible. Lastly, misunderstanding the problem requirements, such as assuming the input is sorted when it's not guaranteed, can lead to incorrect assumptions and flawed logic. Always read the problem statement carefully to avoid these issues. Poor time and space complexity analysis is another area where candidates often falter. For example, relying on an O n squared solution when an O n log n alternative exists can lead to inefficiencies and potentially failing test cases. To perform well in interviews, it's important to clearly understand the problem requirements before you start coding. Take time to confirm your understanding with the interviewer, asking questions about edge cases, constraints, and expected outputs. Communicating your thought process is equally important. Explain your approach step by step, as interviewers value clarity as much as the final solution. Begin with a brute force approach to demonstrate your understanding, then optimize iteratively to show how you handle trade-offs. Use examples to validate your approach, walking through test cases manually to ensure your logic is sound. Finally, Be prepared for follow-up questions, as interviewers may challenge you to handle additional constraints or optimize further. Practicing adaptability is key to succeeding in these situations. When preparing for this problem, it's helpful to explore related problems that share similar concepts. For instance, toSum, longest substring without repeating characters, valid parentheses, and merge intervals are all excellent examples from LeetCode. Solving these can help you recognize patterns and build transferable problem-solving skills. In terms of alternative approaches, the brute force method is a straightforward starting point. While it's simple to implement, it comes with the trade-off of inefficiency for larger inputs due to its high time complexity. Another option is using a hash map or hash set, which can significantly improve time complexity to O(n). However, this optimization may increase space usage, so you'll need to weigh the trade-offs based on the problem's constraints. The sliding window technique is another efficient approach for problems involving subarrays or substrings, though it requires a careful and precise implementation to avoid logical errors. Divide and conquer is another powerful technique to consider, especially for problems with a recursive structure, such as merge sort. This method is highly effective but can be challenging to implement and debug, so it requires a solid understanding of recursion. Binary search is another excellent strategy, particularly for scenarios involving sorted data. Its efficiency, with a time complexity of O log n, makes it a go-to approach for many problems. However, it does come with its own challenges, such as carefully handling indices and boundary conditions to avoid off-by-one errors. Mastering these techniques and their trade-offs will not only help you solve this problem but also prepare you for a wide range of algorithmic challenges. That's a wrap. We reviewed the Encode number problem, explored the solution space, and highlighted key takeaways. I hope you found this session insightful. Remember to stay curious and keep practicing. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!